Hello.
Hello, what's up?
Okay, what are you doing right now? A puzzle? What are you doing? Okay, well,
5,000 pieces.
it's not puzzle time, it's podcast time.
Oh, is that right now? Okay, I'll get on right now. Bye.
Okay, all right.
Hello? Can you hear me?
Yeah, okay.
Oh
good.
yeah, what's going on? I'm ready.
What are we talking today? These two, I don't even know what you call them, meteorites?
Yeah, these are people who study meteorites. It's, very interesting how these things develop, how they find them on the Earth, that kind of thing.
But you said there was an article. What grabbed you about the article?
I found this article about these two scientists who found this mineral that didn't appear anywhere else on Earth. I thought it would be pretty interesting for us to talk to them. I think we should put them on.
I'm excited. I'm ready to see what we're going to learn or find out something.
Thank you guys for doing this. Appreciate it. So what does it mean, this discovery, this mineral you found on a, what does it mean?
So,
Go ahead, Chi.
I assume Jesse is talking about Edscottite, right? So that famous for 2 days and last year regarding this publication. So this is Edscottite is a new iron carbide mineral. So it's only the third iron carbide mineral ever found in nature. So it's pretty interesting. And it was found in a very old, kind of relatively old meteorite from Australia. And our friend, our colleague, Ed Scott, actually he observed this phase in 70s during his Ph.D. research. And he figured out the chemical composition of this phase, but was not able to understand its crystal structure at that time. So
Let me give a bit of background on this, if I may.
Yes.
One of the, there's different kinds of meteorites. One of the meteorites that this one is called an iron meteorite. Most iron meteorites are from the cores of asteroids that melted. Just like the Earth has an iron core, asteroids that melted have iron cores as well. Most asteroids did not melt, but those that did have iron cores. And the pieces of those cores are iron meteorites. They're chunks of the cores that have landed on the Earth. They've also landed on the Moon and Mars, by the way. One of them, which was found in Australia in 1951, was called Wedderburn because it was found near the town of Wedderburn in Australia. And Ed Scott, a colleague of ours during his PhD dissertation in Cambridge, was studying this meteorite because he studied iron meteorites, and he found this new phase. But because of the primitive technology at his disposal back in those ancient days, was not able to properly characterize it. And so it wasn't till just a couple of years ago that Chi, with his sophisticated modern analytical equipment and expertise, was able to finally and properly characterize this phase.
So now why were you guys looking at that? If it was from the 70s, why did you think to go back and check it out again?
That's a great question. And I'll let Chi talk about that in his techniques in just a minute. But let me just say that every new mineral has a story to tell. And understanding how this thing formed gives us a new story about how this particular iron, because of its composition, because of its cooling rate from high temperatures, how those conditions combined to form this unique phase, which is not found anywhere else in nature. So let me just say that minerals form under many, many different circumstances. Some minerals, the oldest ones in the solar system, formed when the solar system was originally a cloud of gas and dust that was cooling. And as the gas cooled, minerals condensed from the gas as solids. Because the pressure was so low, they condensed as solid grains. And these grains are the oldest minerals. They're 4.56 billion years old. They're the oldest minerals in solar system rocks. Other minerals formed just like in lavas as rocks crystallized from a magma. Other minerals formed as some of these asteroids were altered by water trickling through them. Others formed by heating. Others formed from pre-existing minerals as they cooled from high temperatures in their crystal structures that were no longer able to accommodate certain of the minerals in them already. this particular mineral, Edscottite, is a new iron carbide, and it tells us the particulars of the formation of carbide minerals under particular conditions. And
so do you guys find it funny to be always calling your friend's name when you're talking about the mineral?
no, not really, because each of us also have minerals named after us.
What's your mineral called?
My mineral is called Rubinite,
Yeah.
and that I had no part in its discovery because you're not allowed to do that. And Chi has a mineral also in his honor. And let me just say something about Chi, and I think it'll be very interesting for him to
But
talk
what's
about.
Chi's mineral called?
Well, let's ask Chi. Chi, what's your mineral?
Chi will tell you that in just a second. But let me just say before he tells you that, no one, perhaps ever, has discovered as many minerals and characterized them as he has. And he has discovered, most of the minerals he has discovered are from meteorites, but he's also found new minerals on the Earth as well. And he can tell you a little bit later about all his incredible techniques for finding these, and they can also describe about his mineral and mine and where they're formed. So,
Well, what's your favorite mineral named after you called Chi?
Oh, so I have so far discovered like more than 40 new minerals, most of them from the meteorites, and some of them are pretty important. So one of them is called Bridgmanite. It's a high pressure mineral. The Bridgmanite is so-called silicate perovskite. It's the most abundant mineral in Earth, as make up the 38 volume% of Earth. So people realize we have this silicate perovskite in the lower mantle since the 70s, but only until recently. I have a collaborator and we spent like 5 years track down this Bridgmanite. Now we named Bridgmanite. It's a silicate perovskite, also in a meteorite from Australia. So it's a high pressure, high temperature mineral. So it took us like 5 years to figure out and also get approved. And means we named the most abundant mineral in Earth. That's one of our research highlights. So it's kind of
Chi,
what's your mineral named after, Chi? What's your mineral name? I'm sorry, go ahead.
Okay, a mineral named after me is by a scientist from University of Hawaii. So the name is Machiite.
Now, when you guys are going to look for meteorites, do you,
Right.
what do you like? Because I understand you're doing diagnostic tests on the meteorites, but when you want to find meteorites, where do you go to look?
Well, Chi and I look in our labs.
Yes.
But let me say more broadly that meteorites fall randomly all over the Earth. But there are certain places where meteorites are found in greater abundance than other places. And these things are deserts, hot deserts and cold deserts. About 20,000, no, actually, no, about 37,000 meteorites have been found in Antarctica on the ice.
Because it's easy to spot them?
They're easy to spot, and they're also concentrated there. Meteorites fall there, and they get buried by the snow. It doesn't snow often, but it snows occasionally. Get buried by the snow, and they get deeper and deeper and deeper. The snow and the ice flows downhill, as everything does, and when it reaches certain places where the transantarctic mountains are, the ice wells up. The wind blows away the snow, and the ice sublimates, just leaving the meteorites stranded on the surface. And so these particular areas, which are called blue ice areas because they've been scoured free of snow by the winds, by the powerful winds, the meteorites are just scattered there, and you can pick them up by the bushel baskets. Although they're not picked up that cavalierly, but there's many thousands of meteorites that have been found there. Other places are like in the Sahara. Most of these are called Northwest Africa because we're not sure exactly where they're found. But NASA sponsors teams that go down to Antarctica every southern summer to pick them up. And various nomads now have a good thriving business picking up meteorites in the Sahara and then bringing them to mineral shows where they sell them to dealers.
well, I have a question. Well, first of all, how do we know that they're real and they're just not like picking up old dung or, rocks? I mean,
Old dung.
well, that's kind of codified or something. See, she likes that. He understands what I'm saying, that maybe that could be it. Like,
I think she's being polite. I don't think.
No. Here,
Yeah.
let me explain. No, I understand your question
you know what I'm
perfectly.
saying? Like, who gets to determine what a meteorite and how to authenticate it?
Yeah, me. I am a meteorite authenticator, and every week at UCLA, I've retired recently, but every week at UCLA, I would get dozens of specimens. We call these things meteor-wrongs because they're not meteorites. And as a geologist, I can tell what a normal rock looks like. In most instances, I can say, oh, this is a basalt, this is a sandstone, this is a granite, this is a shale or whatever, because I can recognize the rocks because I've been doing this for close to 50 years. But some things you can't tell for sure. And in those cases, I will cut off a piece of it and then analyze it and look at its composition, mineral composition, or its texture. And in those cases, we can see, it doesn't match that of a meteorite. For example, metallic meteorites will have iron, will have a 5 to 10% nickel generally, and a little bit of cobalt, and will not have other minerals like chromium and manganese. Whereas terrestrial steels and slags will generally have little nickel and will have chromium and manganese. And so by checking their compositions, we can tell what they are.
I have a question. What is it? What is exciting about it? What is a meteorite? Why do you both find yourself so in the focus of it? What is exciting? What does it tell us about the world we live in? Like, why do I care about a meteorite other than it's going to come down? And I have.
Okay.
You know,
I'm going to say something and then I'll let Chi talk because I'm much more bombastic than he. Let's look at the sun for just a second. Shade your eyes. The sun, as we know, is mostly hydrogen and helium. But if you take away the hydrogen and helium from the sun, what you'd still have is a rock that's 6,300 times the mass of the Earth. And the elements in that rock, remember, we took away the hydrogen and helium, all the other elements, sodium, potassium, iron, nickel, cobalt, manganese, praseodymium, europium, silver, gold, tin, all these other elements would have the same proportions, the same inter-element proportions in them as the meteorites do. Now, what does that mean? That means that these meteorites, the most primitive ones, the ones that haven't melted, these so-called chondrites, here's one here, these so-called chondrites, these things are the building blocks of the solar system. These are the rocks that first formed the earliest solids in the solar system. They came together to form the planets, the comets, the asteroids, the sun, all the objects in the solar system. By studying these meteorites, we can begin to understand the origin and evolution of the solar system. Not just that, I'm almost done. Some other minerals were formed in asteroids during impact processes. These are high pressure minerals, of which she has discovered many, and others formed by crystallization in these things. So we can understand the evolution of asteroids, and there's also meteorites from the moon and Mars. And whereas we only have Apollo samples and Soviet lunar samples from a small area of the moon, lunar meteorites come from the entire lunar surface. And the moon is a geologically complex body. So by studying lunar meteorites, we can understand the moon much better than just from the Apollo samples. And the only Mars rocks we have in our possession right now are Martian meteorites. And so, and he has one there, I think, which I'll show you in just a second. So the point of meteorites, the relevance is that we can understand the origin, history of the solar system, the evolution of the bodies in the solar system by studying these rocks.
This one is like slight rock sections of a Martian meteorite called Shogoti Martian meteorite, also very famous. So last month we see 3 missions to Mars, right? We are going to study rocks there, also collecting some rocks. But right now we do have rocks from Mars in our hand, so we can really take a really close look.
Chi, would you show us your lab?
Yeah, sure. I would. Okay, allowed to.
So
okay, let me put my.
It sounds like one of the things that you've developed is new diagnostics to see things that previously might have been overlooked. Is that what you're studying? Like a new way of looking at some of these things?
Yes, something like that. So okay. So I'm kind of like pathfinder in the field called like nanoscience.
Mm-hmm.
That means nano meteorology in my field. So basically, is we study minerals, we study rocks down to nanoscales.
Mm-hmm.
So back to our beginning story regarding this Edscottite, this is like a great example of how this science can advance by analyze old rocks with new techniques and fresh ideas. So, okay, so
is there a place where there's just thousands and thousands of samples and you could just, I saw when you held up the Mars rock, it looks like it's cut to look at it on a microscope or something. So
right.
Is there just thousands and thousands of samples that have, lying around where you can go like, what is this? They say it's this, but maybe it's something else?
Yes, so I have thousands in my office, in my lab at UCLA.
Mm-hmm.
Do rocks ever die? I mean, do they ever disintegrate? Not die, okay, don't look at me like that, Alan, okay. But what I mean to say is there ever a end date where they just sort of disintegrate, or these rocks from billions of years ago, or, or do they just always adhere to the?
No, as soon as the rocks start going through the atmosphere, they start to deteriorate. They are formed under low oxygen conditions, and when they reach the oxygen-rich atmosphere of the Earth, where there's water even, they start to weather away. So even a freshly observed fall will begin to rust, and they can rust in the cabinets. The meteorites begin to rust and weather away, and after a certain amount of time, they can crumble into putrid dust, and you won't be able to see them anymore.
Okay, thank you. Do you think of them as living? Do you think of them as something, you have such a relationship, both of you, to these forms? Do you think of them as, beings?
No, I don't ascribe any sentience or life to them. But she has his labs there now, and he can talk.
Great, thank you for taking.
So one question, the Earth is 8 billion years old.
4.56.
4.5 billion years old. What's a few?
Jesse.
But so if everything on the Earth is of that age,
it is not.
Right? Okay, so what do you how do you think about that?
Okay, all the planets in the solar system formed at about the same time, 4.56 billion years ago. However, the Earth is a dynamic place. There's wind and water, which breaks rocks down. There's plate tectonics, rocks get subducted into the mantle. There's volcanic eruptions, new things form. And so the oldest extant rocks in the middle of continents are about 4 billion years old, 4.2, maybe there's a few rocks that old. Nothing survives from the beginning of Earth history. And almost all samples are just millions or a few hundred million years old. Very few are anywhere near the age of the Earth itself.
Do we understand why the mountains go up? Do we understand why the Earth is not? Because if we're spinning in space, wouldn't it just be an exact circle? And why we have all this geographic variation of heights and things?
Well, there's differences in heat between some places and the others, and that drives the Earth is divided into 12 major plates, which is these are called lithospheric plates, which is the crust and upper mantle. And these things slide across one another because of convection currents in the mantle. Even though the mantle is mostly solid, these things slide on a layer called the asthenosphere, which has a few percent silicate melt in it. And so these things slide, they crash into one another, causing mountains. They slide past one another. Wherever these boundaries converge or meet, we can have earthquakes. And let's just think of this for just a moment. If we have a solid, brittle crust on top of something which is a little bit fluid, the fluid will flow smoothly, but because of friction, the solid material above it will get hung up and won't flow along with the stuff underneath it. And then the strain gets higher and higher and higher until it has to be relieved. And when it's relieved, we have an earthquake. And so we have a place like Mars, which has no plate tectonics. Then you have a hot spot coming from the mantle. We just have lava flowing in the same place. Just gets higher and higher and higher. We get Olympus Mons, this huge volcano on Mars about the size of the state of Arizona, which is over a stationary hot spot. Whereas on the Earth, the plates slide over the hot spots. So we will get the volcanic islands of Hawaii, for example, and the Emperor Seamount chain, which is because the Earth slides over the hot spots, so we don't get volcanoes that are that big.
Okay, Chi, take us to your lab here. What's happening?
All right. So now it's within our electron microscope lab. This is called field emission scanning electron microscope. So basically, we use electron beam strike a specimen, producing a spectrum of signals. We use different detectors pick up signal to form electron image. So that allows us to look at the solid materials down to nanoscales. And also we can do micron analysis. At the same time, we can do structural analysis, crystal structure analysis.
Is this a super expensive process, or can you just sit in there all day long looking at different samples because it doesn't cost you a lot of money to do it once you have this expensive machine?
Yeah, once you have it, then okay. So because this is such important for anyone dealing with solid material analysis. So on our Caltech campus, we have like almost 10 SEMs like this. This is one of them, most popular one on this campus. Also, we have many users from JPL to use this instrument. And this is also, of course, one of my key, like a gaming machine for discovering new minerals.
Do you have is your name on it somewhere so nobody can take it home?
Yeah. Okay. I'm going to do this after this Zoom meeting.
Yeah. So what are we looking at now, Chi?
So okay. So right now on the screen, there's a real sample inside. It's a iron-day meteorite. Okay.
Can you
so
get
actually,
a little closer? Can you bring your camera a little, your computer a little?
Right. Okay. So
there you go.
this is okay. So this is like a scanned backscatter electron image. Now we see a contrast. Those contrasts are different mineral phases. I'm still working on because this is a new mineral. So it's a mineral puzzle I haven't been able to crack yet. So this is a different, it's called meteorite, it's a silicate. And okay, I can talk about more regarding this iron-day one. So iron-day meteorite fell in like 69. Yeah. 69, right? So
February 8th.
Most studied meteorite in human history. So our current understanding about early solar evolution is heavily based on intensive study of this rock. So anyone who studies meteorite, they must study iron-day. So is that important? But until last year marked 50 years of iron-day, and we have a special meeting and have a journal special issue to mark this occasion. And still nowadays, in every journals for meteorite research, they have papers on study of iron-day meteorite. So it's very important. So it's also, so I'm still studying that since 2007 and still making new discoveries. So it's very exciting and yeah, lots of fun.
When you look at that, and I guess you're saying that the area in there that's white is not, you said I haven't cracked it yet. What does that mean?
Not a known mineral, not identified. That means I figured out its chemical composition as a chemical formula, but so far I was not able to fully understand its crystal structure, how the atoms, oxygen arranged at atomic.
Let me just clarify something if I can. There are certain minerals which have the same chemical composition as each other, but have different crystal structures. They formed in different ways under different conditions. And there's a number of minerals like that. And so even though he knows the chemical composition and knows it's a titanium oxide, and there are other titanium oxides, this formed in a new way, and he doesn't have the crystal structure yet. When he gets that, he'll be able to better define how the phase formed.
So what's the challenge of getting the crystal structure?
Yeah.
Is this the wrong tool? Is this, you need something, is it like, at CERN, you need more and more power and it needs to be bigger to look deeper in down into the structure of the matter?
That's a great question. Okay, the limit here is the crystal size. Because the crystal is at this some sub-micron size. Okay, like say, the human hair diameter is about 100 microns. 100 microns.
1,000.
So, right. And
it's a millimeter, 1,000 microns.
Mine are bigger, but I understand what you guys are saying.
okay, I think average 100 microns. Okay.
Maybe your hair's
All right.
thicker than mine.
Mine's a little bit, but I understand what you're saying.
Okay, so some of the new minerals we have discovered, they are also the rarest minerals we ever discovered because they're at micron scale, maybe 1 micron or 2 microns. Sometimes for those sub-micron crystals, they're just too small for us to do a clean structural analysis. So at that case, we were not able even to use a synchrotron diffraction in those regional labs for X-ray structural analysis. And also the phase I'm working on is not only like a new mineral, it's also a new type of material that never ever synthesized before. That's mean brand new to science.
You know,
So
so
some of
go
yes.
ahead, Chi. I'm sorry, I interrupted.
So some of those new minerals are also new materials. And one mineral is called pangolite. It's also one of the oldest mineral in our solar system from in the solar nebula. And it has a really complex chemical composition. When we look at the formula, it's oh, it cannot be. Nature couldn't have this kind of phase. Now we see that, and we approved. Then later I have the one collaborator. I say, oh, how can if we could perform this synthesize in a lab, and we did it. Yeah, we somehow synthesized that. Now those kind of minerals also provide useful information for material scientists to engineering maybe new type of materials. Yeah, so that's.
So, you know, a lot of people understand, they think they understand that science understands every single thing in the world. But what you're talking about is a scientific theory. And what does that mean to keep searching for newer and different innovations? What does that mean for the theory of science, the higher calling of science?
Oh, so I love science, and science to me is just a game. When I came to school every day, I'm like, oh, new game. Okay, so it's a never-ending journey. I would say for everyone, that I would say that's a beauty of science, and also I love nature. I love basic science.
Let me just say that in scientific meetings, we follow the dictum, don't get even, get mad. And so we see people get very irritated with one another at scientific meetings because although they may be looking at the same data sets, because of the large uncertainties and the different emphases one researcher may put on a particular data value than another, there's an awful lot of controversy at the frontiers of science as to what something means. So they can be very vitriolic and contentious going to these scientific meetings because it's not something, here it is, everything's clear, everything's settled, let's go on to the next thing. It's rarely like that. When you're at the frontiers of science, there's a lot of contention, a lot of uncertainty, and a lot of screaming going back and forth for years or decades before something finally becomes settled.
And it can be settled until there's a new theory that...
Absolutely. That's right. Sort of like a paradigm shift, as the philosophers of science might say.
You know, how do you see faith as different from the theory of science? Why is science itself, the Enlightenment, such a different idea than we had before?
Well, before I get into strong language, maybe Chi can give you his opinion, which I don't know.
Yes, I don't know. I'm just enjoy nature and love science and really enjoy what I'm doing, and feel I can contribute a little bit to science. So I really enjoy it.
Are you running for office? Because that was a very political answer.
Okay, wait. Chi, you love science, and you said it, and I can see you're both unbelievably passionate. It's fantastic. But why ultimately did you go down into this particular area? What is it about this that you do? This specific with the meteorites, with the rocks? Like, what is it that grabbed you? You probably could have done a lot of different things, but why this?
okay, I'll try to answer the previous question and answer this one as well. No, I want empirical data before something is can be at least temporarily accepted. I want to believe as many true things and as few false things as possible. So with science, we have data. And the good thing about science, as opposed to religion, is that it's changeable if new data comes along. There are no permanent verities. And so if you look at Hebrews 11:1, where it says, these are the things of evidence hoped for, the things unseen, you can see that just means faith is wishful thinking. Science can't survive that way. Science is based on evidence. And if you have faith in something and the evidence doesn't support it, you're going to get shot down by one of your colleagues. And so we really have to be on our toes all the time and be sure that the evidence supports what we say. And I think that's the closest path to asymptotically approach truth.
That was well said. And did you see me virtually clapping on that?
And I wasn't watching. I was just too absorbed in what I was saying. So.
Plato and the shadows and verifying them.
Well, I think you say an incredible thing, which is there is flexibility. Perhaps what you're saying is it's something is a fact or a truth, and then we are still open to discovery, and then we can change. Whereas potentially in religion, it's not necessarily that way. We have
scientists don't use the word belief very much, and they don't use the word truth, maybe ever. They will just say, if they're behaving properly, they will just say that here's the evidence, and we believe that this is what it indicates. And it could be strongly supported or just moderately supported, and it's subject to revision.
Okay.
And that's always the case.
We're going to let people know that you said that, since this is a podcast. But Chief, why the meteorite? Just going back, one last thing. What is it that captured your heart?
Okay, so I was a terrestrial guy. Okay, study Earth materials for my PhDs and postdocs, and then later on, as I mentioned, just by chance to beginning to study adjunct meteorite, because it's so different compared with terrestrial rocks. Then after I study adjunct meteorite, and then I beginning to just for fun, playing with other famous meteorite. I like to study those very famous meteorite because they are well known, well studied. All the background stories is already there. So I just examined basically just for fun. So, but in my case, once I start, let's say, to me, it's just a book. A rock is just like a book. When we take a closer look at it, in my case, down to nanoscales, I always say something new, something excited. So then, once I have a new mineral, then there's a voice, there's a story. Then it fit, just providing a piece to the puzzle of our understanding about, like say, our early solar system evolution. That's in the case of Ayande. So it's just very exciting. And I just cannot stop.
Let me ask one last question. When you guys find these things and you get an insight, does it change any of the mystery? Does it take any of the mystery out of it for you, even if you've learned, you've unlocked some secret to it, but it's like, is it still a mysterious, wondrous kind of thing?
We know such a tiny fraction of what's out there. That's no. I just want to say that my approach is very different than that of Chi's approach. I look at things also on a very large scale to see how things may fit together, what the textures of the rocks are, how the different large class may fit together. So I may look at things that are tens of thousands of times, hundreds of thousands of times larger than the scale that Chi looks at, because that's also part of the same story. And all this has to be put together to make a hope of understanding how these rocks formed and what they tell us about their parent bodies.
This was fantastic. I don't think I've ever heard a rock compared to a book. I mean, that is an incredible way to think about it. I can't thank you both enough for coming in.
Yeah, wonderful, you guys. Thank you for coming
wonderful. In. And Alan, you need to stay cool. You can take your shirt off after this is over and go back to whatever was going on there. You stay safe, both of you. And we hope to see you again Zoom. That was my bad pun, but hopefully we can be in the real world and come and see some of the work that you're doing in the other world. Thank you.
Yeah, you're
Thank
welcome
you,
to visit
guys.
us.
Well, let me just say that when UCLA reopens sometime, we have a very nice meteorite gallery, and someday we'll reopen, and I invite you guys to come and see it.
Thank you.
so much.
Thank you guys very much.
See you
Yeah,
later.
thank you for having us. Yeah.
Okay, thank you.
Guys,
Yeah,
Bye-bye.
these guys are fascinating.
They're really fantastic, and I think Alan has a life as maybe a host of a series.
He probably does it already.
Don't you think?
Yeah, he probably has his own
Okay, what did you
podcast.
learn today that you did not know before? Anything?
Just all the things about, rocks, how they develop, how old the Earth is, and how we think about different things on the Earth. And, I thought they had a lot of very magical thinking that I thought was quite unusual, both of them, in different ways,
Yeah. I especially liked that science, religion thing. Conversation was fantastic.
Yeah.
All right. That's it.
Okay.
See you next
Nice
time.
to see you. Okay.